So for part B, we're going to calculate this same volume using the shell method. So again, I'm going to quickly redraw the sketch. So we've still got that region bounded by the parabola y equals x squared, by the x-axis, as well as the vertical line x equal 3. And we're still revolving that area there a bit around the x-axis. So we're still creating that same volume as before. Now this time we're going to calculate using the shell method, which means taking slices that are parallel to your axis of revolution. If we're revolving around the x-axis, we're now going to have these horizontal slices. So let's imagine what's going to happen when this horizontal slice is revolved around the x-axis. What we're going to be tracing out is this sort of a shape here. Okay, so it's a hollow shell. And let's think about the dimensions of this shell. So this shell here, it's got a radius, it's got a height, and it's got a little bit of thickness. So let's think about the radius first. How far is this top point from the axis of revolution? Well, that's going to be y. Let's think about the height of our shell. At first it might be tempting to say x, but if you look back at this horizontal slice here, you can see it's actually ranging between two different curves. So it'd probably be a little bit better to call that x2 minus x1, just to indicate we're going to have to go the right curve minus the left curve to get that height there. And then our little bit of thickness, if you're imagining like a can of soup or something like that, the thickness is going to be the thickness of that actual metal, the thickness of the shell itself. It would be dy, since it's a small change in the y direction. Okay, so we've got our dimensions. Y for the radius, x2 minus x1 for the height of the shell, and dy for the thickness. Now, for the shell method, dv is going to be 2 pi times the radius times the height times the thickness, and that represents the volume of this hollow shell here. So let's plug in. So we'd have 2 pi times y times x2 minus x1 times our thickness dy. Now what's going to happen is that we're actually summing up all of these different hollow shells here that we're creating by taking all these different possible horizontal slices. So each horizontal slice here is going to generate a different hollow shell, and by summing them all up, you'd be creating the total volume of your solid. So v is going to be the integral then of dv, and we need to make sure that we're integrating through the correct values. The dy here tells us that we're going to be integrating with respect to y, and if we look at the y values that we're ranging over, it's 0 to 9. So I could say v is the integral from 0 to 9 of dv, or more explicitly I could just write in what dv is, so I think I prefer to do that. V is equal to the integral from 0 to 9 of 2 pi times y times x2 minus x1 times dy. Now notice that we're going to be integrating with respect to y here, and that means all the expressions inside this integral have to be in terms of y. In particular, we need to get x2 and x1 in terms of y. So if we look back up at our sketch here, let's look at the two curves, x1 being the left curve that's bounding this area, and x2 being the right curve. So x2 is equal to 3. That's constant. And so technically you could say that's written in terms of y already, so that's no problem. But we'll have to do a little bit of work to get x1. So x1 being this curve that's bounding the left side of our region. So we've got y equals x squared. If I write that the other way around, you could say x squared equals y. Or taking roots of both sides, you could say x equals, technically we have to say plus or minus root y when we're taking roots of both sides. But I'm going to cross that off, and we know from our picture that we're talking about positive x values since we're in the first quadrant. So it's safe to write x equals positive root y there. So that's going to be the curve that's acting as our x1. That is the left curve that's bounding our region there. So now we've got x2 equals 3, x1 equals root y, and that was just a little bit of extra work that we had to do here because we were integrating with respect to y. So now we're ready to go back to our volume. So let's use all this work here now to rewrite v. Just recopying from down here. V is equal to the integral from 0 to 9 of 2 pi y times x2 we've said is 3, and we're going to be subtracting off x1, which is root y, and that gets multiplied by dy. So now to get this volume calculated, let's bring the constant 2 pi out in front. We've got the integral from 0 to 9. And at the same time, let's multiply through this expression because we're not going to be able to integrate the way it's written here. We need to multiply out. So we've got 3y minus, now if we multiply y times root y, that's like y to the 1 times y to the 1/2. It's going to give you y to the 3/2 because those exponents are going to add there. So we're getting 3y minus y to the 3/2, and that gets multiplied by dy. Okay, that was a bunch of work. We're now ready to actually do our integration. So we'll leave the 2 pi out in front, and integrating we get 3y squared over 2 minus, on this term here the power is going to bump up, y to the 5/2, and we'll just be multiplying by the reciprocal of that exponent. So there we go, and that expression is going to get evaluated at 9 and then at 0. So our volume is 2 pi times the following. We're going to have 3 times 9 squared over 2 minus 2/5 times 9 to the 5/2. Okay, and I really want another set of brackets on here. That's our value at 9, and then we need to subtract off our value at 0. So the square brackets are indicating that 2 pi is multiplying everything through here. Round brackets to show we've evaluated at 9 and then evaluated at 0. Now fortunately, this expression inside the square brackets works out exactly if you plug it into your calculator. So you can check, that comes out to 24.3. And so indeed our volume works out to 48.6 pi. And you can compare it to the answer that we got using the disk method. So certainly both answers are the same. They're both calculating the same volume. So they've got the same value there. And in this particular problem, I would say the disk method was a lot easier. But depending on the problem, sometimes the disk method is easier, sometimes the shell method's easier. So we really want to be comfortable with both methods.